Welcome to The Explainer. Today, we're diving straight into the microscopic mechanics of chemical bonding. We're going to bypass those high school basics and take a much closer look at the intricate rules and honestly, the fascinating exceptions that actually govern atomic attraction.
But first, we gotta ask, why do atoms combine in the first place? Why not just chill and exist independently? Well, under normal conditions, literally no element naturally exists as an isolated atom, with the exception of the noble gases. You see, systems naturally tend toward their absolute lowest energy state. Bonding is really just nature's built-in thermodynamic mechanism to attain that stability.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the quest for stability, then the Cussell-Lewis octet rule, move on to covalent bonds, ionic bonds, check out some octet exceptions, and finally wrap up with measuring bonds.
Section 1. The quest for stability. Nature's way of lowering energy.
The absolutely crucial point here is that a chemical bond is fundamentally an attractive force. It's that simple. When atoms form molecules, they're held together by this invisible pull. Whether it's atoms or ions coming together into a single species with its own unique properties, it's this attractive force doing all the heavy lifting to keep the whole group stable.
Section 2. The Cussell-Lewis octet rule. Setting the ground rules.
Way back in 1916, two scientists, Kessel and Lewis, independently revolutionized our entire understanding of chemical bonding. They noticed that noble gases were highly inert. They just didn't react. Why? Well, because they already had a perfectly full outer shell of 8 electrons. And from this observation, the legendary octet rule was born. It simply states that atoms are going to combine, either by transferring or sharing their outer valence electrons, specifically to achieve that highly stable configuration of 8 electrons in their outermost shell.
Lewis initially pictured the atom as a positively charged kernel, which was just the nucleus plus the inner electrons, sitting inside a stationary cube. He actually imagined that the outer valence electrons would literally occupy the 8 corners of this cube. Now, obviously, today we know that electrons definitely do not sit still on the corners of a stationary box. But this model holds incredible historical significance. It gave us the very first real visual framework to understand electron arrangement and the whole pursuit of that stable octet.
Section 3. Covalent bonds and Lewis structures. The power of sharing.
Fast forward to 1919. Langmuir refined Lewis's cubical idea and officially introduced the term covalent bond. Think of it like this. A covalent bond, like what we see in a chlorine molecule, relies on mutual electron sharing to achieve an octet. It's like two kids happily sharing a toy. On the flip side, ionic bonding is a complete transfer. One atom just gives the toy away entirely, yielding an electron and creating a localized electrostatic attraction between a newly formed positive and negative ion.
Now, when you're mapping these out with Lewis dot structures, there's a really logical flow to it. Step 1. You start by pooling together all available valence electrons, making sure to adjust for any ionic charges. Step 2. You draft a skeletal structure, putting the least electronegative atom right at the core. And finally, Step 3. You establish your single bonds and distribute the remaining electrons to fulfill those octets. And hey, if you run short, just convert some of those lone pairs into double or triple bonds. Now here's a super fascinating concept: formal charge. Sometimes you can draw multiple valid Lewis structures, right? Well, formal charge helps us find the absolute most stable one by assuming perfect electron sharing. For instance, calculating this little math trick for ozone leaves the central oxygen atom with a +1, while the ends are 0 and -1. To be clear, it doesn't mean rigid charges actually exist there. It's just a tool. The structure with the smallest formal charges is almost always our true lowest energy molecule.
Moving right along to Section 4. Ionic bonds and lattice enthalpy. The magnetic pull. So, we established that ionic bonds involve transferring electrons, which creates positive and negative ions that attract each other like magnets. But there is a massive factor at play here called lattice enthalpy. By definition, this is the energy required to completely rip apart 1 mole of a solid ionic compound into its gaseous ions. What this really tells us, the so what here, is that the 3-dimensional crystal lattice structure is what firmly locks ionic compounds into place and gives them their incredible stability. The numbers involved here are pretty wild. 788 kilojoules per mole. That is the lattice enthalpy of standard everyday table salt, sodium chloride. Think about the thermodynamics for a second. It actually takes energy to turn sodium into a positive ion, and the energy gained by chlorine accepting that electron, it isn't quite enough to balance the books on its own. It's actually short by about 147 kilojoules per mole.
But when these ions snap together into their rigid 3D crystal solid, boom, it releases a massive 788 kilojoules per mole of energy. Ultimately, that huge release of energy during the formation of the 3D crystal lattice is what truly drives ionic stability. The energy released more than compensates for the energy absorbed, creating the ions in the first place. So this gives us a really great visual contrast. Whereas covalent bonds create distinct individual molecular shapes based on sharing, ionic bonds build these continuous, incredibly rigid 3D lattice structures.
Section 5. Exceptions to the octet rule, when the rules fail.
Now, what's really interesting about this is that the octet rule, while incredibly useful, especially for second-period elements, actually has some major rebels. First up, incomplete octets. In molecules like beryllium hydride or lithium chloride, the central atom is perfectly stable with fewer than 8 electrons. Then we've got odd electron molecules like nitric oxide. I mean, they simply can't satisfy an octet for everything because the total number of electrons is an odd number. It's just physically impossible. And what about expanded octets? Elements in the third period and beyond, like sulfur and sulfuric acid, have extra 3D orbitals available, which allows them to comfortably hold 10, 12, or even more valence electrons. And finally, those supposedly completely inert noble gases, yeah, they actually can react. Elements like xenon will readily combine with fluorine and oxygen to form compounds like xenon difluoride. Crazy, right?
Furthermore, as helpful as the octet theory is, it has two massive blind spots. First, it is completely silent on the relative energy instability of a molecule. And second, it completely fails to account for a molecule's 3D physical shape. Because of these pretty significant limitations, scientists had to look further to map out the actual spatial reality of these chemical bonds.
Which brings us to our final section, Section 6, Measuring Chemical Bonds, Length, Angle, and Enthalpy. Since Lewis dot structures don't really show us physical reality, how do we actually measure it? Well, first we look at bond length. This is the measurable physical equilibrium distance between the nuclei of two bonded atoms. If the atoms are sharing electrons in a covalent bond, their cores actually overlap slightly, which we measure by their covalent radius. But atoms also have what's called a van der Waals radius, and that represents the overall physical size of the atom's valence shell in a non-bonded situation. To put that into perspective, we literally use techniques like X-ray diffraction to physically map out these tiny microscopic distances. We also measure the bond angle. This is the angle between the orbitals containing the bonding electron pairs around a central atom. And let me tell you, this metric is absolutely critical because it dictates the real-world geometry of simple molecules. For example, by measuring the specific angle between the hydrogen and oxygen atoms in water, we know for sure that water isn't just a straight line. It has a specific bent shape. This distribution of orbitals is exactly what bridges the gap between those simple 2D dot structures and the actual physical 3D shapes interacting in the world around us.
We've definitely covered a lot of ground today, from atoms desperately seeking out an octet, to sharing versus transferring, right down to the massive energy of 3D lattices. But I want to leave you with this one thought. If bonding at the microscopic level is simply nature's way of seeking stability and lowering energy, what unseen connections, what vast complex networks of atomic structures are quietly holding together the materials around you right now? Keep questioning, keep learning, and I'll catch you in the next explainer.